Okay, let's start today. So we'll be continuing our discussions on the Fourier transform, and yesterday I had given you the two important relation of the Fourier transform calculation. So one is that if you have the time series data, then you just try to write it in this integral, and then you will be getting the Fourier transform of this one. So this is what we call it as a Fourier transform of the function t, or the time domain function. And if we already have a frequency domain transformation, then you can multiply it with e to the power I omega t, and then you will be transferred back to the time domain, right? But there is only things you can understand, that there is the phase part of the signal is gone. So you can only get the amplitude part, but not the phase part, because in the Fourier transform, whenever you take the Fourier transform, the absolute value, then you lost the phase part. We'll come to that point afterwards. So if it is a time domain, say suppose anything, it might be the pressure with the time. So there is the amplitude is 100, and the number of cycles in 1 second is basically, say suppose 200 hertz. You can calculate, because there is one cycle and there is another cycle in a 10 second. So its frequency is basically 200 hertz frequencies, right? So if you can use that, then you can have in the time domain, if you see, then you will be seeing an amplitude of, the amplitude is 100, which is basically this one. So the amplitude of the frequency, amplitude of the wave is 100, and you will be getting a point. So this is your 200 hertz, right? So at that point you will be getting the amplitude. So you can find out that this signal, which is the time domain signal, this time domain signal has a input, has a amplitude of 100, right? So that's, you can calculate directly, right? So any function, you can take e to the power I omega t, and then you can compute the Fourier transform of it. So if you can use your this function, a function which is t less than equals to 1 equals to 0, and t greater than 1 is all 0. So that means the functions looks like this way. So at t less than equals to 1, this is basically all are basically one function, or the unit function, and after t greater than 1, this is all becomes 0. So if this function is like this, then you can do this integration and put the values and calculate the functions like this, right? And similarly, if you take the inverse Fourier transform, then you will see that you will not get 1, but 1, half, and 0. At t equals to 1, you will get a half, and then after that t greater than 0, it will be this one. So although you started with this function, but in your if you take the reverse Fourier transform or inverse Fourier transform, you will not recover the entirely the signal, right? So the signal will not be identically as we have got it before. There will be little bit difference, and that difference is due to the phase and all other part. We'll come to that point afterwards, how we have to do this. Okay, so the impulse function, if it is an impulse, so impulse is basically your you know, the impulse function is basically delta t is basically impulse functions, right? So this is your impulse, means at time t equals to 0, this is a pulse like this. So if I multiplied these things with a delayed impulse, so that means delayed by an amount d0, then ft, if I multiplied with a delayed function, then this will be equals to ft0, right? So that means the function, instead of a t equals to 0, it becomes the at t equals to t, t0 values, right? So that's your function, because I delayed it by delta t0, so it is a 0 elsewhere. So if I can do these things, so ft is a continuous, and so therefore if we can take this part, then it will be at the point t. So that is your impulse, the Fourier transform of the impulse part, right? So if you can put that, if your delta t equals to 1, then you can take these things at a different point at t equals to t0. If it is a delta t, at this point we will be getting a step functions, which basically ut0 in this way, right? So you will be getting a functions which might be like this way, right? So if it is a f delta t u0 dt, then if you can do that, and then it will be getting a unit impulse function ut0, right? And if it is a so it converts to a, so delta t0, if you can do the differentiation, it will be this function's differentiation, it will be giving you a dt0s, right? So if you have an exponential function e to the power j omega 0 into t, and if you can take the inverse, take the Fourier transform, so Fourier transform of e to the power plus j omega t plus minus. So if you can put it here, then what will be this function? So these functions will be equals to, if it is a j omega 0 into t, then it functions will be equals to t 2 pi delta omega plus omega 0. So a Fourier transform of an exponential function will be a shifted delta function in the frequency domain, right? So so if we have the exponential functions, it will be so Fourier transform of a e to the power plus minus j omega 0 into t, that will be equals to, this is 2 pi delta of omega plus minus omega 0. So that's the things you should remember it. We'll be coming to this point again afterwards. Now there is another thing is basically is very important in the Fourier transform things. It's the Parseval's theorem. So Parseval's theorem says that if we can calculate the energy means it's basically the amplitude square, right? So amplitude square. So if it is a ft is the signal, and that ft you make it a square, that becomes the energy, or it is a power, right? So if I take this minus infinity to plus infinity, this ft square dt, so that will be equals to 1 by 2 pi of the Fourier transform square into d omega, right? So the amplitude part, or the amplitude spectrum, will be also get basically the power part, right? So f omega square. So if you take the square of these things and take the energy, then energy will have a Fourier transform of these things. So So between omega 1 to omega 2, if you try to calculate it, so this is your minus omega 2 to minus omega 1, and then omega 1 to omega 2, if you can calculate it, then it will be it is basically a real valued function. So 1 by 2 pi into f omega squared d omega, right? So, so if you have a sinusoidal signal, so sinusoid means it is a e to the power jx and e to the power jx by 2, and sin x means e to the power jx minus e to the power minus jx by 2j. So if you can take the Fourier transform of any cosine function, so it is a cos omega 0 t. So this is the plus part, and this is minus part. So that you have to do the Fourier transform, and by that formula, whatever we have done it earlier, that if you can use that, and this divide by 2, so the 2 pi will be gone, and then for this part, this will be equals to plus omega. So that means these things will be pi delta omega 0 and pi delta omega plus omega 0. And similarly, the cosine omega 0 t, oh sorry, I take it back, this will be the sine. This will be the sine omega 0 into t, that it will be minus and 2j, so this is pi by j, and this is pi by j omega plus this one. So if it is a sine functions like this, it's a omega 0 is the frequency of the sine function. If you take the Fourier transform, you will be seeing at this point, at the minus part, there will be a value which is the amplitude is minus pi, and this side there is a plus pi, and that is here, and this is a complex plane, and this is the real values, right? So that will be the sine omega and cos omega t. This will be the function. So next part is the properties of Fourier transform. So Fourier transform is a linear property. So if it is a ft has a Fourier transform of f omega, okay. So if that is the case, then if we multiply the function with the a f t and take the Fourier transform, then it will be a into f omega. So that's the part. So if I have a ft has a Fourier transform f omega, and gt also has a Fourier transform of g omega, then bgt will have a Fourier transform of b of g omega. So that's just a scalar multiplication, and if you add both the things a f t plus b gt, then they will have a Fourier transform of a of f omega plus b of g omega, right? So this is your linear and addition, they will be all together. If it is a plus or minus, then this will be also plus and minus, right? So this is what we call it as a linearly. So Fourier transform has a linear property. The Fourier transform also have a time scaling, right? So if ft has a Fourier transform, if any function has a Fourier transform of f omega, then if we multiply the times domain by a function ct, then it will be equals to 1 by c of f omega, right? So it will be 1 by c of f omega by c. So that will be divided by the c factor if it is a. So that means that in the scaling property, if you can do this one, then you can calculate it will be equals to 1 by c f omega. So if I have a shifting of the time series, if the time series is shifted by an amount t0, so that means if this is your ft, this has a Fourier transform of say f omega like this, might be that is your f omega, okay. So this is your ft has a Fourier transform of f omega, then ft minus 0, so that means it is shifted by an amount from here to here by an amount of t0. So then the Fourier transform has to be multiplied by e to the power I omega 0 t. So whatever is your Fourier transform here, that you need to multiply it with some number. It will be equals to e to the power j omega into t0 into the f omega value. So whatever your f omega was, you have to multiply it with e to the power j omega t0 if you shifted the scale by a t0 amount, right? So you can put these things as a proof. So ft, the Fourier transform of ft minus 0. So I put this function first, and then I multiplied with e to the power j omega t, because that's a Fourier transform form. So this ft omega 0 is basically, you can change your t minus t0 with a value of t, and then you can shift the t minus t0 as equals to u, and then write it t equals to u minus of t0, and then dt will be equals to du, because t0 is constant. So then dt I will be replaced as a du, and this t minus t0 equals to u, and this will be equals to, I had already put it as u values. If you put that number and calculate these things, this will be omega minus, this will be equals to e to the power I omega t0 into this function is basically your f omega. So that is equals to e to the power I omega 0 into this part, right? So that's the proof. That means if your signal is shifted, then the amount of time you are shifting it, that you have to multiply it with omega and multiply it with the Fourier transform values. Okay? So this is your time shifting. If it is a frequency shifting, that means just a reverse one. So if you multiplied your time series now with the e to the power I omega t0, then in the Fourier domain it will be shifted by an amount of omega 0, right? So that's your frequency shifting theorem. We will be using this frequency shifting theorem a lot of time. So you just put these things, take the inverse, take the Fourier transform of this one. So I omega t0 is there, and ft into e to the power I omega t is this much. So if you can do that part, so this will be equals to f omega minus omega 0. So this will be here, right? Now there is a symmetry theorem which says that if the ft has a Fourier transform of 2 pi f minus f omega, right? So if ft has a Fourier transform of f omega, say suppose some function, say suppose a box function has a Fourier transform of a sinc function. So then if I take a sinc is a t function, time function, then this will be equals to 2 pi of minus f omega. So that will be equals to 2 pi of whatever is the f omega was. So that will be multiplied with that one, right? So if f has a Fourier transform of ft has a Fourier transform of f omega, then if I take the f as a t, that means this is a sinc omega, then sinc as a t, then it will be 2 pi of f minus omega. So that means this will be equals to box 2 pi of box minus omega values, right? So this is what I am seeing it. When I am seeing it here, so this is your box function. It becomes a sinc functions, right? So this is your ft. It has a Fourier transform of f omega, which is a sinc function, and then I take the sinc function as a time domain. So this is your sinc t. Then your Fourier transform will be multiplied. If this is equals to 1, then this function will be multiplied only by 2 pi times. So that will be the symmetrical function. So that is a symmetry property. So that means if a rectangular pulse is there, it will produce a sinc pulse. Then if you take the sinc pulse then it will be produced the rectangular pulse but multiplied by a number 2 pi in front of it. Okay. So this is your there is another property, is called modulation property. So ft is a, if ft has a Fourier transform of f omega, then ft multiplied by cosine omega 0 t, so this will be the multiplied with a cosine omega 0 t, it has a Fourier transform of f of omega plus omega 0. In case of a cos, this is your plus of f omega minus omega 0. In case of a sine, this will be minus thing. So omega plus omega 0 and omega minus omega 0, that will be done if it is modulated by any cosine functions, right? So I have a proof here. Now the differentiation in time. So if ft has a Fourier transform of f omega, okay, and then if I try to differentiate it, so that means f dft dt, so that means the Fourier transform of f dash omega, f dash t, when it will be equals to I omega into f omega. So this is I omega into f omega. So that means whatever is the Fourier transform of the original pulse, if you take the differentiation of that pulse, then you will be just multiply by the I omega in the Fourier domain, right? So if the displacement has a Fourier transform of f omega, then if you can calculate the velocity will have a Fourier transform of whatever function it is, you just multiplied it with a j omega. Okay, so that means if you calculate acceleration, then acceleration will be equals to minus omega square f omega. So you need not to do anything, you just multiplied it with your omega square, you can get the corresponding Fourier transform of the acceleration pulse, right? So this is your, so time differentiation, if you do a time differentiation from displacement to velocity and from the velocity to acceleration, you are multiplying it with your omega, or might be a omega square if it is a double differentiation. So since you are multiplying here, therefore what will happen, it will be enhances the high frequency, enhances high frequency values. So that means if your displacement pulse has a frequency content, and then your acceleration pulse will have a more high frequency values. Okay, so time differentiation enhances the high frequency component. So the noise will increases if you take a differentiation of the signal, right? So that's your proof for the frequency differentiation. Now if I do a integration, then it will be the straightaway division of the things. So that means your ft, if it has a uniform thing of the Fourier omega, then your integration of minus infinity to t ft dt will have a, so this is your integration part. If we do the Fourier transform of it, then that Fourier transform will be 1 by j omega into f omega. So whatever is that, we just divide it with your j omega. So the pulse will be divided by the j omega. So if you have an acceleration pulse and you take a Fourier transform, you compute the Fourier transform of an acceleration pulse. Okay, let's see, this is your a omega, then your, let's see, this is your at. So at has a Fourier transform of f a omega, then your vt has a Fourier transform of 1 by j omega into a omega, right? So that means you divide the pulse, whatever you obtain from the acceleration data, by the j omega, and then take the inverse transform, you will getting the velocity. If you need to do a displacement, then you need to do a double differentiation. So this is 1 by j omega square of a omega, right? So that will be equals to, this will be equals to minus of 1 by omega square into a omega, right? So that's your part. So you are dividing with the omega square. So basically you will be seeing that this pulse will be changes its shape, right? So in case of your any acceleration data, you take the Fourier transform of your acceleration data, you will be mostly seeing the pictures like this. This will be the picture of an acceleration pulse, or this will be shape of the acceleration pulse. It will be just like this, then this, and then this, right? So this is your some corner frequency. Now if you do the double differentiation, this pulse will looks like a functions like this, where this will be the FC values, right? So this now becomes this one. Earlier that the acceleration pulse was like this, so then the displacement pulse will be like this one. So then you can inverse do it to calculate the displacement values of the time domain, right? So this is your frequency domain of the acceleration data. Then if you take your divide by 1 by square, then you will be getting a displacement pulse, and then you take it inverse Fourier transform, you will be seeing a displacement values like this, right? So then it becomes a displacement dt. So a omega by j omega square equals to 1 by dt, right? So this is very important relation, this frequency division and integration, because we all always like to calculate from the acceleration pulse to the displacement pulse, or by the displacement or the velocity pulse to the acceleration pulse. So then we can use these two frequency, the integration property and the differentiation property, to calculate the Fourier transform, right? Now the convolution, I have shown you last time the convolution things. So convolution between the two signal f and g, if I say that they are convolution, then that convolution, if we take the definition of convolution, so that means this will be equals to minus infinity to plus infinity. Then this is your f of f convolution g, so f of tau and g of t minus tau, right? So that will be equals to d tau, right? So f tau into g tau. So f convolve with g, then this will be, this is actually the pictures, right? So if you can do a Fourier transform of it, so that means minus infinity to plus infinity, and then do the Fourier transform. So f convolution g, the Fourier transform will be the frequency transform of the f multiplied the frequency transform of the Fourier transform of the g function. So just multiply. So this is your convolution product. This is your convolution product, but this will be equals to a multiplicative product. So this is your multiplicative product, Okay, so a convolution is simply a multiplication in the frequency domain. Okay. So that's that is our day-to-day use for the the interpretation of the seismogram, because whenever the seismogram get recorded, recorded at a station, right? So this is your seismographic station. We record a seismogram. Now this seismogram is the product of the source function. So this is your source. It is coming here, and then it has propagated to the path and then interact with the machine, right? So all these three events, source, path, and the machine, they all in time domain, they all convolve each other and then can produce this signal. So that means whatever recorded signal you see at your site, this actually a multiplication of source function, then it is a convolution of source function, convolution of the path function or path data in time domain, and then the convolution of the machine function or the site function. We call it this one, right? So in the time domain, they are all convolution things. So it is a time domain convolution, this is time domain convolution, path in a time domain form, and then source as a time domain. So this is your recorded signal in this case. Now if you take the recorded signal Fourier transform, so that means this is your recorded signal Fourier transform, so that means it goes to the frequency domain. Then since it's a convolution, if you take the Fourier transform of it, so then it's the Fourier transform of this function multiplied by Fourier transform of path function multiplied by Fourier transform of site function. Okay, so this is source function, site function, and this one. So this, I should not write it here. So these are basically your source path, frequency, then the path frequency, and then site frequency. They are all multiplied each other instead of a time domain convolution. In the time domain convolution, it will be in frequency domain. If you multiply the spectra, then that spectra will be the spectra of the recorded signal. So that is where we are using the convolution product in our calculations. Okay.
Elaborate the site function. What does it mean?
Site function. Okay. The site function is basically whenever the earthquake happens, then earthquake comes through the material of the rock mostly, and then whenever it comes to the some sort of a machine, it get amplified, right? It get amplified due to the low velocity sediments present compared to the rock, and it get amplified. And so that amplified product or that machine amplification is actually reflected on the recorded signal. So the recorded signal is also modified based on the type of the sediment present in that particular site. So therefore, for all the signals, say suppose you have a station, say suppose one station is is at this side. So this is located on a rock, and these are basically located on a different alluvium part, right? So this is your station 1, this is your station 2. So these are the station on the alluvium sediment, or might be any sedimentary part. Now let's see, this is your earthquake happens here. So this is your earthquake or the source, right? So it registered here, it has gone and registered here, it has gone and registered here. So all three sides, all the part has been registered, and then there is a time history, as you have seen last day. So that type of time history you can see there, right? But let us assume that the earthquake is a very far distance, and all these stations are within the city. Say suppose one is here, other is in the Hirapur, other is in the Bankmore. So compared to the distance of the earthquake has happened, let's say earthquake has happened near the Himalaya, and then these stations, the distance are more or less the same, right? Because that will not change as much. But what will change is basically the response of this alluvium basin, because this is this much, this might be much more, and this is at a rock. So they will not amplify, but this will be amplified, and that we need to take care of it. So what we do, we take the one part is this, to do the time domain modeling. So time domain modeling means if you know how this pulse has been created, and then we can do the time domain calculations and calculate it here. But please remember, this time domain calculation means it is basically the convolution of each other, and then convolution calculation is not a very easy one. So what we do instead, as a replacement, we take the full Fourier transform of it, and that Fourier transform is basically whatever the source Fourier transform multiplied by path Fourier transform multiplied by site Fourier transform. So the multiplication is much more easier than taking a convolution thing. So that is what we are trying to do here. Okay.
Depends on the geology of the underlying structure, and what is path?
The path will attenuate the high frequency waves. So basically, as it passes, then so whenever there is an earthquake, it will created a signal. So that signal will have all frequency present. Every frequency is present there, right? So because it's a pulse, right? And but whenever it comes to the site, you will be seeing that the records are like this. So that means the records are all from all the records, the high frequency part is gone. So high frequency part is attenuated as it travels. Now, so that you can see the pulses in the recorded signal, right? If you see a very close distance earthquake, you will see the close distance earthquake will have a pulse like this. But if you have seeing a very teleseismic earthquake, then the teleseismic earthquake will have a pulse like this. Because the teleseismic earthquake, when it travels, it will all attenuate the high frequency component of the signal. It will have only the low frequency part, and that low frequency comes to when it comes to your recording station, and you record that. But so that is the effect of the path. It will have a effect of the attenuation and the frequency attenuation as it travels. More it travels, more high frequency get attenuated. Okay, so
Every time you will get attenuation, or the attenuation is also possible.
The attenuation is also possible.
In one case
so
if the same soil, if we have a because the soil always have some non-linearity present. So sometimes what has happened that if the earthquake is very strong and it strongly affects the sedimentary or alluvium, now what has happened, the water present in that has been get displaced, and as a result there is a amplification noticed, de-amplification is noticed over certain region, because if the water is not there, then it is a solid material, right? So then it will not amplify that much. So it will go a de-amplification. But that is called the nonlinearity behavior, nonlinear behavior of the soil. So if it is a very strong earthquake, you will be seeing that same site which was showing a little bit amplification at some particular frequency, it will show now a de-amplification at that particular frequency. So that is also possible in some of the soil type. Okay? Huh? Source के बारे में? So what do you want to know? Yeah, so basically that will be the in the earthquake, in the dynamite explosion, as I said, it is a very impulsive source. But in case of your the source can be like this way. The source, it will be just an impulse. It will be just an impulsive source like this.
we recorded from all data, but how to extract it is source data, source bars, and
In the recorded signal, whatever you record, it is a combined convolved product of source, path, and site, right? So that is no doubt. But the question is this: that if your source is a certain type of impulsive source, then your signal will be different because your source part is different, right? But if it is an earthquake, then also you can see it here. It will be a pictures like this. It might be a rise, and then it will be stable like this. It could be a function like this. It could be a function like a big rise. Okay, so this is your rise time, and then the rise time might be a finite rise time. The rise time might be a impulse type of rise time. So these are all are basically the source type. So source function, if you can say the time domain function of the source, if you simply put it, then it could be either of these. Okay, and then what has happened? Say suppose this is the fault, and this is the epicenter part, and then this fault gets ruptures, and it will be propagate some distance. So as it ruptures, so each and every point will emit the energy, right? And that will be getting complicated with this one. So that means the one part will be like this, and then other part will be the rupture part, and and they will be convolved with each other and produce a trapezoidal type of pulse. So that we will be discussing in our source modeling, that how the source function can be modeled, and how from the source function how can in a time domain a signal can be generated, and how the signal can be generated in that. So that will be coming after that. I think the next week we will be doing that. But for the time being, we make our life a little bit simple by taking the taking the spectra of the data, because the spectra, it is a much more easy to handle, in the sense, computationally it is much more easy to handle because it is just a multiplication. So we can find out the multiplicative things much more easier than doing the convolution part. Does it make sense to everybody? So all the, when everybody is trying to do that, they need to, because our main interest is to understand what is underneath that particular site, and for that we calculate the 1D velocity structure from the recorded signal. Yes, that is what we always do. Okay. So in the calculation of the Fourier transform, whatever we have so far said, it's basically the mathematical development, right? So that's the mathematics. Mathematicians like to do it with all the integration, differentiation forms, and they love to do that. But we need to calculate the things, right? So we need to compute it with the basis of our data, right? So how to do that thing? So that's computationally easier things to do is basically what we call it is a discrete Fourier transform. So the Fourier transform is the Fourier transform that is a mathematical part, but how to implement it in a computer and how to do it in a computer, so that is what we have to understand. So that is what we call it as a discrete Fourier transform. Now discrete Fourier transform, in some way it will be modified later. It is called first Fourier transform. So first Fourier transform is actually the how to calculate a lot of sample data much more quickly. So that is your basis of the first Fourier transform algorithm. So that algorithm we have developed, and we can calculate a FFT, via FFT, these things will be implemented in a computer. But this FFT is actually based on the discrete Fourier transform theory. Okay, so we know that if we have a signal and that signal has been sampled at the different places, at the different time domain, and then if you take the Fourier transform of it, we like to see that sorry, not the Fourier transform. So then ultimately we are getting a discrete values like these, right? So that is what you will have in your computer, right? So a discrete value, just like yesterday you have seen that is all the time and then all the acceleration values. So similarly that way, these are discrete values, and yesterday you see that it is a 0.005 second interval, all the data are there, so that you will be getting it, right? So we express the time domain, actually the time domain signal, which is in this form, as a discrete functions of the xn, right? So xn is basically goes from 0 to n minus 1, because there are n number of samples. So let us assume that we have a 0, 1, 2, 3 up to say n minus 1 number of samples are there. So this is 0 to n minus 1, or we can say it is n number of data, right? So 0 to n minus 1 samples means actually taking the 0 also into the account. So we will have a n number of samples. N is the capital S is the number of samples. So therefore what we need to do is that we know that we have multiplied e to the power minus j into omega into t, so that t part we are basically doing it with your jn into k, and this n value go from 0 to n minus 1, and this will be the xk. So that means first value in the frequency domain, it is a k equals to 0, k equals to 1. So that way it will be equals to this 2 pi when omega into t, that will be written like this way, right? So therefore, if you take the inverse Fourier transform, then xn you can calculate if you know the xk value, and then it will be the plus 2 pi j into nk by n, right? So that's the part for the discrete Fourier transform, right? So if you say that xn equals to, if it is a 2, 4, minus 1 and 6, and n is the number is the 4, so the capital N is the number 4 because we have 1, 2, 3 and 4 samples. So that means n equals to 1 is 0, x value is 2, n equals to 1, x value is 4, at 2 this is equals to minus 1, at 3 this is equals to 6, right? So that's the values. So xk will be equals to xn into e to the power j pi by 2 into nk. So then you can write it like this way. So these same things you can put it here. So 2 pi nk divided by n, so n equals to 4. So if you put the 2 pi j into n into k divided by n, and n is equals to 4, so this is your j pi by 2 into j pi by 2 into nk, right? So that n equals to 4 means it is a j pi nk divided by 2, right? So that is what we are doing it here, e to the power minus this. So that's your minus value, and that will be equals to minus j e to the power minus j. These things is basically j into n to the power k, right? Because minus j pi by 2, you can calculate it will be j pi by 2, and cos pi by 2 and sin pi by 2, so it will be minus j, this one. So x0, if we can put x0, so that means in the frequency domain, this is x0, x1, x2 and x3. So you can see here that the first value, if you can put here from n equals to 0 to 3 and this number, so this will be the 11, then 3 plus 2j, then there is a minus j, and then this is x3 equals to 3 minus 2j. So these are the form you can see it in the Fourier domain. So actually the Fourier calculation is done by this way, but they will be implemented a much more faster way of calculating, because you are doing it with a suppose 24,000 data, 25,000 data. So how to do it much more faster manner? So they do by a fast Fourier algorithms. So that's a FFT algorithm, and that is what we need to use in our either in MATLAB or in a Python, whatever you are using it, you have to use that manner, right? So if we say that this is your sine function, right? So this is your sine function. So I discretize the sine value from 0 to 2 pi, because this value is 2 pi values. So I discretize the sine values with a pi by 100. So this many of samples we have done, and then x will be equals to 0 to 2 pi, with each one is being sampled at a pi by 100 values. So then if you can plot it, it will be like this, right? So this will be the sine functions. Now if we can use your frequency, let us see if it is if your sample frequency, so this is your sample frequency is 150, so then your t will be equals to say minus 0.5 to plus 0.5 with a sampling frequency of 1 by fs, right? Say suppose this is your box. This box, I like to calculate the Fourier transform of this box. So first of all, I need to sample the box at some discrete samples values. So this is equals to fs 150 sampling frequency. So our time domain, it will be say from minus 0.5 to plus 0.5, but it has a time domain, it will be 1 by of fs, right? So delta t will be equals to 1 by of your fs or the sampling frequencies, right? So that is your this one. So we have divided it into this many of times, and then the w is equals to 0.2. So that means this value equals to width of these things is 0.2, and this x will be equals to, this is your some sort of a MATLAB command. This MATLAB command will create a pulse like this with a 0.2 width and with this t value. So if you give this many of t values and ask it to calculate a 0.2 width rectangular pulse, so from the 0 point, they will create a rectangular pulse of 0.2, right? So let's see, we have now the time domain function which is discretized or digitized at 1 by fs second difference, right? And let us see, I have number of data which we like to use is basically 512 data. So that means in the frequency domain, I need to have a total 512 data. So that is your length of the data available, right? So and this length we need to be a always 2 to the power n type of length. So that means either it will be 512 or might be 1024 or might be 2048. Now suppose your data is now having a 1400 number of sample data, right? So you have a 1400 sample data, so you will be putting it at a 20448 should be your NFFT, so that you are basically adding all the zero, because it has been found out that the first Fourier transform will be done much quicker way if the number of data points is the 2 to the power something, right? So that way it can be done quickly. So what we do, that we will be, if your data is not say 2048, because it is not possible to always have a 2048 data points. So say suppose if you have a data point, say 1024, 1400 data, so number of data is 1400, so it will automatically be transformed to the 2048 by adding zeros after that, right? So that the computer will automatically do that things, okay? So that, or you can put it, or you can instruct the computer that, hey, take that next power of 2. So whatever is the next power of 2, you can take that number. So 1400, you will go to the next power of 2 is basically 2400. Or if you have a data, say 640, you can go up to 1024 number of data points, right? So always give a 2 to the power something format. So that's your NFFT, and then you give your data values. Okay, that's fine.